We try to help companies to innovate and to really applicate the technology in the industry. So we do all the validation and the innovation process until we see that the companies really master the technology and can apply the technology by themselves. It's mainly based for Belgian companies, but we also are doing research projects at the European levels, and we work also with European companies in France, in Germany, Sweden, etc. There are 4 main domains in series: the ICT domain, materials, advanced manufacturing, and mechatronics. Here, we are in the additive manufacturing department that is inside the advanced manufacturing field of domain. It's very nice because additive manufacturing is something that is related to materials, is related to mechatronics, is related to powder metallurgy and to other manufacturing techniques. Well, in the additive manufacturing department, we are a team of 20 people with something like 25 years in additive manufacturing field. We have more than 10 technologies in-house, different. We have the machines, and we really produce parts, and we help the companies to understand the limitations and the advantages of adopting the additive manufacturing technology. Now I would like to speak about the process chain of the additive manufacturing. Additive manufacturing is another manufacturing technique which has really a lot of advantages compared with other manufacturing techniques, but you need to have a know-how in this technology as in any other technologies. 2 things I would like to avoid that you think. Additive manufacturing is not just press and play, at least for industrial scale. We need to really implement design, understand the limitations of the technology, understand the main benefits to unlock the full potential. And indeed, it's not only having a machine and then you are done. As other technologies, there is a behind and after processing that you really need to master. So at the end, there is a full chain that you really need to optimize in order to unlock the best potential of this technology. Well, here I propose a manufacturing chain, but it's just an example. It can be different for the type of application of the parts that you really want. Everything starts with the design. If you really want to unlock the potential of additive manufacturing, you need to think on redesigning your parts, because normally the parts that you have now are already optimized for conventional techniques that has many limitations in geometry. Additive manufacturing has much more freedom in design. So now you can think and try to redesign those parts. By redesigning the parts, you are going to improve the performance of the part. Before, for conventional techniques, due to the limitations in the design, some performance of your part was not the best. Now you can improve that. One example is for the heat exchangers. You can add internal lattices in the heat exchangers. You can play on with the internal channels, and you will improve the behavior and the thermal behavior of your heat exchangers. Indeed, there are massivity constraints and some other design limitations in additive manufacturing metal nowadays. This is something that is continuously evolving and improving more and more. Second step, you should be aware of the technology. Here I'm only speaking about electron beam melting and selective laser melting that we have in series. We have more, we have cladding or Prometal technologies, but I would like to compare both technologies here. Electron beam melting is based on an electron beam that is really melting your parts. Previously, you are applying a preheating step of 700 degrees. So we call these processes working like hot bed powder bed. This is going to decrease the range of solidification between your solid powder and your melt powder. This is better in order to reduce thermal stresses. Indeed, for SLM, there are also more thermal stresses, but there are strategies, playing with the scanning strategy, doing thermal treatments to reduce the stresses as well. Normally, SLM allows to do finer structures, have, let's say, a better roughness, and there are more materials already available in the state-of-the-art of additive manufacturing of metals. There are like 12, 13, 14 materials already developed for selective laser melting, but this is something that is continuously evolving. So every day, not every day, but every year, new materials are being optimized for selective laser melting. In the case of electron beam melting, nowadays we have titanium, Inconel, and cobalt chromium mostly. But it's also possible to try with other materials like copper, for example. You need to really understand the technology, and in order to position your part in the best way possible to avoid, as said before, residual stresses that can appear, or to decrease the amount of supports. Supports are structures that are needed when you build a part. It's not the same amount of supports that you use for electron beam melting or for selective laser melting, but anyway, you will need to have supports. Also, you have to think that there are some limitations if you try to build parts, for example, completely horizontal. There are more chances to have deformations. So you have to think how to orient your part in order to have a compromise between a good quality and also a good building time. Supports. Supports are what you can see there, and they have two functions. First function is to really support the structure that you are building, and the second one is to evacuate the heat from the part that you are building towards the building plate. It's not the same, the supports that you need for electron beam melting, that normally you need less supports because in the preheating step you are already pre-sintering powder, so your powder bed is acting like a self-supporting bed, and that is not the case in the SLM. But anyway, you need the supports to evacuate the heat. You have to think that the supports will affect the roughness of your part. So there is a link between the orientation and the supports always, that you have to really understand what are the main surfaces of your part, the functional surfaces, or the parts that are not so important and that also you can post machine. Indeed, in the manufacturing process, there are a lot of parameters that play a role. Nowadays, the main suppliers of machines provide a whole package for the materials when you have the machine. But you can always play and you need to know the basics that is behind for these parameters in order to act for your particular application part. Here I just show 4 main parameters that are the most important, but there are many others. I will say the laser power to melt, to really well melt your powder, the scan speed of the laser that will affect the quality of your melt pulse and also the productivity of your batch, the layer thickness that will be important for the roughness and the quality of the material again, and the hatch space, that is the distance between 2 laser tracks. The palette of materials, we can speak about tool steels, stainless steels, aluminum alloys, titanium 6-4, but also titanium pure, copper, which is something in development, and it's a challenge to produce pure copper, and other materials like tungsten or tantalum. Well, it's always easy if you know the main parameters to create matrix of optimization in which you vary the main parameters, and you can afterwards, through a metallurgical analysis, determine the best properties for the materials. So it's something that even if you don't find the material in the state of the art, you can always try to develop yourself the material. Indeed, this takes some time of research. The powder that you will use it's important. Normally for SLM, the size is between 10 and 60 microns. It's important that the powder is spherical, and also the flowability of the powder. You need to really spread the powder well with your recoater in the machine. Electron beam melting is using bigger powder and plasma atomization techniques normally. Just to compare the size of the metal powders with some things, just to make you an idea of the size of the powder. Indeed, here we need to take care of some security measurements for the operators that are playing with the machines. About the mechanical properties and the quality of your parts, this is a microstructure of an aluminum alloy. What I can tell you is that the microstructure of additive manufacturing of metals is much more finer due to the rapid cooling that you have. You are melting with a laser so fast and solidifying that you are able to really homogenize your phase distribution and have a very nice microstructure in terms of mechanical properties. You can see there a matrix of aluminum and eutectic with silicon. And if you compare with casting, you will see that it's much more fine. And this will have a reflect in the mechanical properties of your alloy. Indeed, you will find, and you may find, sometimes if you don't have the right settings, defects. For example, there are 3 types of defects that you may encounter, speaking in general. You can have irregular pores. That means that you are not applying enough laser power. You can have spherical pores that can come from moisture in the powder or from the argon that you use during the process. And you can have keyhole pores that appears when you really apply too much energy. The good thing is that normally with good optimized settings, and for a lot of materials are already standardized, you can have parts that are fully dense with less than 0.5% of porosity and with mechanical properties that at least are equal than the properties of conventional techniques. We have to think that these techniques will need thermal treatments sometimes, especially for removing thermal stresses that may appear during the building due to these fast cooling rates. In conventional techniques, we apply also thermal treatments, but here we have to take into account that the microstructure of the additive manufacturing of metal is much more different than the conventional techniques. So you need to really apply thermal treatments that are different than the already standardized thermal treatments for conventional materials. There is also already developing an state-of-the-art for different thermal treatments in additive manufacturing of metals. One advice that I can give, for example, sometimes you don't see the residual stresses, and then when you post-machine or when you remove the parts from your building plate, you will see a big deformation. So always apply the thermal treatment, if it's possible, in the build plate. For the post-machining, you can take advantage of additive manufacturing of metals and try to really design structures like can be lattice or supportings that will allow you to hold your part during the post-machining step to clamp really your parts. So take advantage again of the freedom of design and the easy way to add features on your metallic parts in order to make the post-finishing much more easy. Now I would like to show you some real parts that we have done. And these parts are parts that really are going to fly or are flying already, and in which we try to take advantage of the potential of the additive manufacturing, especially in the design. Well, this is a part done in collaboration with Thales Alenia Space, and this is an original part. Here we try to use the topological optimization in order to reduce the weight of the part. The initial mass was 457 grams, and we try to go to 200 grams. This is a big advantage for the aerospace companies in terms of fuel saving. Well, in topological optimization, I'm not going into deep, but basically you need to have into account a first initial volume space, and you need to know those parts that you don't, those areas of your part that you don't really want to modify because they cannot be redesigned. Indeed, you need to know also the load cases that you will apply. Then you put this in topological optimization software like Topol or Inspire, and you can have a result like this. This is after a finite element analysis. You have this and this. You check that you can really produce in additive manufacturing. You made the modifications that are needed, and finally we were able to produce a part that is suitable and optimized for additive manufacturing of metals, and that is able to save 2 times the weight of the original part. Another case study, again with Thales, is a support structure for an antenna that is going to support the antenna of a satellite that will be placed in orbit. This part was produced in series with SLM, selective laser melting technologies, and with titanium material. Just to give you now an idea that sometimes it's not press and play, even if you know the basics. Sometimes, especially when you have a new part, you need some iterations in order to succeed. Once you succeed, then you can produce as many parts as you want. In the first iteration here, we had a problem of overmelting. The part was too massive per layer, so we had some kind of deformations. We had to increase the angle to decrease the amount of melting per layer. But we face another problem. Even supports were not needed due to the angle. Finally, we need to add a reinforce to avoid those thermal deformations in the leg. And in the third iteration of building, finally, we succeed to produce the parts that will go to the sky. So I will be happy if finally you understand that additive manufacturing is a chain of things that has to be optimized before and after, that has certain know-how that you really need to understand the basics, and always think on redesigning for your industrial parts. That's all. Thank you very much.